Hi, I'm Professor Goins. In this video, I'm going to look at the fundamental theorem of calculus part 2. We'll look at the statement of it, but more importantly, I want to look at how do I prove the theorem. First of all, the statement. If lowercase f is a continuous function, is any continuous function, and capital F is an antiderivative, then the fundamental theorem of calculus part 2, the conclusion, tells me how to evaluate a definite integral. This says that the integral from a to b of f is the antiderivative evaluated at the upper limit of integration minus the antiderivative evaluated at the lower limit of integration. Again, that tells me that to evaluate a definite integral, the hard part is just to find an antiderivative. Okay. First and foremost, we're going to need a theorem throughout the statement of our proof. Recall the mean value theorem. The mean value theorem says if I have a graph, so this blue graph right here, and I look at a secant line through the interval from A to B. So remember, the secant line is a line that simply passes through 2 points on the graph. In particular, if I choose the endpoints A and B, which will correspond to these values up here. But if I look at the secant line, what I can do is I can find a tangent line that's parallel to it. And if you look at this red graph right here, somewhere along here, I can find a point of tangency where this red graph will be parallel to the green graph. And in particular, I'm going to look at the value in between A and B that I labeled as C. C corresponds to the point of tangency. Okay. If I look over here, the slope of the secant line, right, rise over runs, change in y over change in x, that'd be the change in the y value divided by the length of the interval for the secant line. Well, if this green line is parallel to the red line, then that's equal to the slope of the tangent line. Meaning I come up with this equation here where I've got the slope of the secant line equals the slope of the tangent line at C. And this statement right here, which is pretty simple to interpret as just parallel lines, we are going to use throughout the proof of the fundamental theorem of calculus. And in fact, is really the main reason why this is even introduced in a Calc 1 course, is because it's used as a proof, used in the proof of the statement of the theorem. All right, let's get to the proof of the fundamental theorem of calculus part 2. Let capital F be an antiderivative of f. So again, in the statement, we have to have an antiderivative. So let capital F be such an antiderivative. And then for the interval from A to B, I'm going to set up a partition, x0, x1, up through xn. Remember what that is. That's a list of numbers where this represents the left endpoint, this represents the right endpoint, and each of these values, x0 is less than x1, x1 is less than x2. Visually, I've got A, which is x0, then I've got x1, x2, all the way up through xn, which is B. Typically, what we do with a Riemann sum is we'll pick these so that the difference is the same, and we just call it delta x. But ultimately, we'll just look at the norm of the partition, and which would be the largest of these. But we'll get to that here in a minute. All we need for right now is I've got this partition of this interval. Okay, then what I want to do is I want to look at the following quantity. Capital F, remember, is my antiderivative. I want to look at the quantity f of b minus f of a. So this is my starting point. I want to look at the difference of this value. Now keep in mind that does appear over here in the theorem. So ultimately I'm going to show that this quantity I'm starting with is equal to this integral. Okay? Here we go. So f of b is the same thing. This is just a change of notation. B is the same thing as xn. So f of b, f of xn, same thing. F of a is x naught, so f of a equals f of x naught. So this is the antiderivative evaluated at this point minus the antiderivative evaluated at this point. Now what I'm going to do is I'm going to introduce a bunch of terms here. Let me do it in a different color. Okay, I've got f of xn. Then what I'm going to introduce is minus f of xn minus 1. But if I'm going to subtract, I also have to add. So this would be plus f of xn minus 1. Of course, this is equal to 0. And then I'm going to, this would be here, would be the x value in the partition, the very last one. This xn minus 1 would be the previous one. Then I'm going to do the same thing with the one prior to that. That would give me minus f of x n minus 2, but then I'm going to add the same thing, f of x n minus 2. Once again, of course, this quantity is 0. And I'm going to do that all the way down to this last term here, giving me minus f of x1. So I'll put minus dot 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 minus f of x1 minus f, hopefully that's on screen, f of x1, I'm sorry, plus f of x1. That might be close. And then finally, of course, this is 0 as well. And then finally, I have my f of x naught. So this would be minus f of x naught. Essentially, what I did is in between these two terms, I added a bunch of zeros. But zeros in the following way. I take the previous term in the partition. Again, if this is xn, this would be xn minus 1. I added and subtracted the antiderivative evaluated this one, and this one, and this one, all the way down to x1. All those would be 0, and I still have f of xn minus f of x naught. Okay, so let me show you what I'm going to do with that. Okay. Within that long series of terms, I'm going to group things together as follows. So I'm going to take the first term and the second term. And I'm going to take the second term and the third term, so on and so forth. So where the very end would be this term with this term. When I group those together, let me start out by just sort of writing that in as follows. That would be f of xn minus f of xn minus 1. And I'll put some parentheses there that are not needed, but just for visual understanding there. So then plus f of xn minus 1 minus f of x n minus 2 plus dot 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 all the way down to f of x1 minus f of x naught. All I did is I rewrote these two lines by grouping terms together. Now I can turn this into summation notation. This would give me, so what is the pattern of each term here? This would be f of x k minus f of the previous term, x k minus 1. And k runs from 1 up to n. Let's quickly check that. If I plug in k equals 1, that would be f of x1 minus f of x0. That's this one. The very last term in the summation, when I get to n, would be f of xn minus fxn minus 1. That would be this term. So this summation represents all of those. Okay. Next, let me remind you of the statement of the mean value theorem. I erased it. I meant to leave that up there for another minute or so, but let me remind you of just the statement in the mean value theorem. We had f of b minus f of a over b minus a was equal to f prime of c. Remember, c was some value between b and a. What I'm going to do is I'm going to take it and I'm going to rewrite it as follows. All I did is multiply both sides by b minus a. This right here is the version that we need in the statement of the fundamental theorem of calculus. Because look at the inside of that summation right there. Notice I've got a difference of function values. Well, here I've got a difference of function values. That means I can replace this right here with a statement very similar to that. This would give me the sum from k equals 1 to n. And again, so how exactly is this going to get replaced? I've got the difference of function values. So difference of function values is equal to, so this is going to be a derivative of that same function. This would be f prime. What do I plug into it? C. C is some value between a and b. I'll label this then as ck. Ck is just some value between xk and xk minus 1, meaning, for example, between x1 and x2, maybe that would be c2 would be somewhere in between there. Okay. Then it's going to be b minus a. That would be this value minus this value, or in other words, xk minus xk minus 1. So it's just the length of that interval. Now, remember what f was. The capital function f was chosen to be an antiderivative of lowercase f. What that tells me is that since it's an antiderivative, when I when I differentiate capital F, I get lowercase f. That's what an antiderivative is. Therefore, this is equal to the sum from k equals 1 to n of f of ck, because f prime and f are the same function, so the inputs match, right? If f prime of ck, it would be equal to f of ck because f prime and c are f prime and f are the same function. And then I've got xk minus xk minus 1. Let me summarize what I have all on the same line then. So the beginning of this string of equalities and the last thing that I wrote up there. All right, here's where we are. F of b minus f of a. That was the start of the string of equalities. F of b minus f of a is the same as this summation right here. Well, what I'm going to do now, I'm going to take the limit of both sides. And what limit would that be? Well, remember our interval. Let me put this back up here. We had x naught, which was a, x1, x2, all the way up to xn, which of course was b. I want all of these to go to 0, the width of these to go to 0. So I'm building in, notice k equals 1 to n. That means I have xn, I'm going to have, maybe this has 10 terms and 11 terms, 12 terms. So I'm building in infinitely many terms here. And I want the width of each one of these subintervals to go to 0. Now, they're not all necessarily equal widths. Therefore, what I'm going to do is I'm going to take the limit as the norm of the partition goes to 0. Remember, the norm of the partition is just the largest of the widths of the subintervals. For example, if x1 to x0 has width, let's say 1, and x1 to x2 is 1.5, and then the rest of these are like 0.7, etc., then I'm going to say that this width here, the largest one, I'm going to force that to go to 0, which forces every other one to go to 0. Okay, take the limit as the norm of the partition goes to 0 of the left side. That means I also have to do the same to the right side. On the left-hand side, f of b minus f of a is a constant that has nothing to do with the partition. In particular, it's going to be the limit of the constant is the constant. Therefore, the left-hand side is f of b minus f of a. What about the right-hand side? I have a limit as the norm goes to 0 of a Riemann sum. That's what a definite integral is. So that's the rigorous notation for a definite integral, meaning the right-hand side is the integral from a to b of f of x dx. Therefore,